Now, it'll be on in a second. What we have, guys, is a particle. Just listen to it at the start. A particle of mass 5 kilograms is suspended by a a light elastic string which hangs vertically. The elastic constant of the string is 500 newtons per meter. The mass is pulled down a vertical distance of 20 centimeters from the equilibrium position, is then released from rest. Shows that the particle moves with simple harmonic motion. Okay, so let's do this. Go and draw myself a diagram. A diagram with a less chunky piece of string. Now, it's of 5 kilograms, isn't it? So, does anybody remember what is the restoring force again? The restoring force. F equals what, guys? K times L minus L0. Okay, so that's K times its current length minus its original length. It can also be written as K times the extension. Now, when you're talking about the, I'll just call it a green region here. The green region here is to specify that anything below this region, any length below this region has no force. The reason why it has no force is mass, light in extended string transferred the elastic constant string. The mass is pulled down vertically a distance of 20 centimeters from equilibrium position and then released from rest, right? So L0 is this length here, okay? And this length here is basically where basically it's at its natural length and there's no force on the string. A weight is then attached to it, and what happens when the weight is attached to it is it undergoes an extension, the red extension there, and this makes the total length of it to the weight as L, with the red part in particular being the extension. Okay. Now there's a force of tension through the string supporting the weight. The weight is 5G going downwards, okay, and that means that the tension in the string must be 5G's upwards. Because it's at equilibrium, it'll be at equilibrium and then it's pulled down 20, but we're just going to talk about when it's at equilibrium first, okay? What we're going to get is tension at equilibrium. Tension at equilibrium equals 5G. Now, and we said K is what, guys? 500 newtons. So 500 newtons times the extension equals 5G. So what's the extension then, guys? The extension is going to be G over 100. Now, what does that actually mean, the extension being G over 100? Sorry? Yeah, G over 100. Okay? So its extension has to be measured in meters. So this little part here is guaranteed to be G over 100. Okay? Now that we've established that, what then happens after that is this. We then get our rectangle here and we pull it down a further distance. So we actually physically pull the string a bit further down. Oops, don't want that part. So we actually pull it down another 20 centimeters. So what we've done is we've extended it again by a blue amount, which is going to be my 20 centimeters extra. What happens now? Are the forces balanced now? No, they're not balanced anymore. So there's a net force. There's a net force of force up minus force down. Okay? Now, in a lot of cases, guys, remember that the whole point is we're trying to set up the simple harmonic system, aren't we? So we're trying to set that up. So, just want you to be aware, displacement downwards is considered positive. Therefore, we're currently looking to set up, do you remember our mass times acceleration for force? And we're trying to set up our A equals minus omega squared x. this means that the force up minus the force down should be a negative number. So we're, instead of using force up minus force down, because force up is the bigger number, we're going to use force down take away force up. That will force it to be negative, and therefore will slide in with the acceleration equation we're looking for. Because the acceleration we're looking for has to be negative, because it's aiming back up. It's going to go, the force is going to go back upwards, okay? So what we're going to do instead is we're going to go force down minus force up. Okay, and now we're going to set up that system. Net force is ma. What is ma in this question? The mass is 5a. What's your force down? Force down? The only thing going down is what, guys? The 5g is the weight going downwards. Now what's going upwards? We said it earlier on. Your tension in your string is k times the extension. What's the current extension? It's 500. And what's the current extension, guys? It's the red plus the blue, which is going to be g over 100 plus 20. So it's g over 100 plus 20 centimeters. Just 1 second. Here, guys, is, remember, the whole goal is to get a equals omega squared x, and then we can find out what omega is wherever we have. Now the whole problem with that is that we're actually not going to use, we're going to set up a system that works for all x values. Now the x value is 20, but we have to set up a system that will work for any extra displacement x. So what we're going to do is the total extension, it's going to be minus 500 times, that's k times the extension. And what's the total extension now? It's going to be g over 100 plus x. Okay. Next thing after that, we're going to get 5a equals 5g, 500 minus a 5g minus 500x. Then we're going to end up with 5a equals minus 500x. We're then going to end up with a equals minus 100x. Now what's a equal to again, guys? Minus omega squared x. This equation matches the minus omega squared x equation, so executes simple harmonic motion with w squared equals 100. Therefore omega equals 10. So what we're going to get is omega equals 10. Okay, so execute simple harmonic motion with omega squared equals 100, omega equals 10. That's great. Now what we're going to do next is we have to show that the particle moves with simple harmonic motion. Done. So that's all that information gone there. Now find the speed and acceleration of the mass 0.1 seconds after it is released from rest. Now I was thinking about the yesterday, okay? I was thinking about, how do you remember which formula are you using? Is it sine or is it cosine? If you remember a sine function, a sine wave compared to a cosine wave, a cosine wave starts off at its amplitude and bobs back and forth, while a sine wave starts at 0 and wait a second. Sine wave starts at 0 and hits its amplitude when the cosine wave is at 0. So basically, if you're starting at the extreme, it's a cos wave. If you're starting dead center, it's a sine wave. Is that alright? Cos wave versus sine wave, okay? Now, at this point in time, we had a system set up. Our system was basically a line, and we had an area that the equilibrium existed. The area that the equilibrium existed was your original length plus g over 10. So we're gonna just put a mark here for this here. So we'll just put a like a big black dot here. That's the black dot there. X represents the extra extension beyond the equilibrium point. Okay? The extra extension beyond the equilibrium point. Now, you release it from rest now. You're releasing it from rest. What is the amplitude of its motion? Where you release it from compared to the position of equilibrium is the amplitude. So what is the amplitude of this? And we're told we drew it down 20 centimeters, right? Didn't we? Language says 20 centimeters from the equilibrium position. This is in fact telling me that the amplitude is 20 centimeters. Now, somebody rightly said 0.2. How did I know I had to put it into 0.2? It's SI units, and it also specifies newtons per meter here. So there's a conflict in units between meters and centimeters, so I had to resolve that. Now, A equals 0.2 meters. Are we starting from the middle or the end? Are we starting from the middle or the end, guys? The end. So it's a cosine function. It's A cos omega t. Now, x therefore equals 0.2. What's the omega value? 10t. Now, does it give us a time? 0.1 seconds after it is released. And it wants me to find the speed and acceleration. So the whole point is I want to find out what v and a are. That's the goal of the question. What's the only thing I can find out here? I can find out what x is. Its displacement at the point in time. 0.1 seconds in. So, 10 times 0.1. Now this is all radians, so you have to put that into your calculator. Please remember it's all radians. You're going to get 0.10806 meters. Yes, never degrees. Okay? Now, you go to your notes, and then we now know what x is, so we have to find a equation that has v in it. The equation that has v in it is this. V squared equals, omega squared. Omega squared a squared minus x squared. The formula for a is minus omega squared x. Now, phi squared therefore is going to be equal to 10 squared times 0.2 squared minus this number here, 0.010806 squared. Solve v. Is everybody happy that you could put that in the calculator and sort it out? So phi ends up to be 1.68 meters per second. That's for the velocity squared. Now for the acceleration, a equals minus omega squared x, which is minus 10 squared, times x, which is 0.10806. Put that into the calculator, and you'll get minus 10.8 meters per second squared. Does it say the magnitude of the acceleration or just acceleration? You can take it as a positive number. Okay. So, now, A and B are two fixed pegs. A is 4 meters vertically above B, and a mass m kilograms is connected to A and B by two. Keyword, two strings. What does two strings mean? Shared tension or different tensions? Different tensions. So, two strings. Shared tension or different tensions. For what value of W would the tension of the upper string be double that of the lower string? Okay, so I was right. So, T1 and T2. Now, it says, for what value of omega would the tension in the upper string be double the lower string? That's grand. I'll just call one of them 2T, and I'll call the lower one T, because it has to be double it. Isn't that right? That's another way of thinking of it. Now, and choice of formulas. Is this motion in a vertical circle or motion in a horizontal circle? Motion in a vertical circle or a motion in a horizontal circle? It's a horizontal circle. It's like a lasso. A lasso. Okay? So, it's not like the one we did yesterday. We have a different setup this time. Here's the setup we're going to use. We're going to use a centripetal force, which can be mv squared over r, or it can be m r omega squared. Then our second choice is forces up equal forces down. So that's motion in a horizontal circle compared to motions in a vertical circle, the one we did yesterday. Motion in a vertical circle has the conservation of energy. Okay? Now, choice A or choice B? Which one? Choice B specifies angular velocity. Choice A doesn't exist anymore. Now, let's do this. Start off with breaking it up into its components. Okay, now we need to find a bit about the language here. We need to find a bit about the length. 4 meters in total. Does it say anything about sitting dead center? Describe a horizontal but uniform thing like such of equal length. They're equal length. Isosceles triangle. Which therefore means what about the middle, guys? Means 2 meters here and 2 meters here. Do you agree with that? And what does it mean about the angles? Anything about the angles, guys? It means that that's an angle theta. That's also an angle theta. They're both the same. Okay. Now, let's call the length of the string L. So let the length of the string equal L. I'm just going to get rid of the tensions for a second. So, if that's L, what does it make? What's the red length going to be? Anybody know? Let's go for sine theta. Okay. So we'll go for L sine theta. Ends up to be, we'll call this H for a minute. Ends up to be H over L, because L is the hypotenuse. So then H equals L sine theta. Is that right? So that red length there is going to be L sine theta. That's done, and that's still 2t and t. Now let's use Fc equals mr omega squared starting off. So this one here. So what are the forces that are undergoing in the string? We have a tension going up this direction here. So what's going up and to the sides? Going up is what, guys? And that's 2t. So what's this component here? 2t sine theta. Would anybody agree with that? Because sine theta equals, if we call that y, it would equal y over 2t, which makes it 2t sine theta. If I was to label this x, cos theta would be x over 2t, which makes x 2t cos theta. Now, the green string represents the upper string. Now I'm going to do the lower string, represented by a blue one. So, blue string is the lower string. We're going to break that up into its components as well. So, once again, the bottom part is theta, because it's an isosceles triangle. And that's t. So what does that make this side here? It's the opposite side, so what are we using, sine or cos? It's the opposite side. Sine. T sine theta. This one's the adjacent side, which makes it, anybody? T cos theta. Now, okay, now FC, force. What forces are driving it towards the center of the circle? That is going diagonally left down. So what forces are driving it towards the center of the circle, guys? Yeah, it's going to be your 2t sine theta plus your t sine theta ends up to be your m. Now what's our radius? Our radius is L sine theta, isn't it? So radius here should be L sine theta. Yeah, the radius of the motion is L sine theta. And then omega squared. Okay. Now, 1 second. In the notes I have. Now, what happens next, guys? It's 3t sine theta ends up to be m l w mu squared sine theta. What happens to the sine thetas? They can cancel, and we just get 3t equals ml omega squared. Okay, store that. That is not forces up versus forces down. That's the centripetal force equation. Now I'm going to work on forces up versus forces down. Now, what forces go down, lads? What forces go down? Usually the weight of the object, isn't it? Making it mg. That explains why the upper tension is always going to be more tense than the lower tension, because it has to support the weight as well. Okay, so forces up equals forces down. So what's the force going up, guys? Force going up, anybody? Look at your diagrams here and here. So we're going to have 2t cos theta, and then what goes down? Mg. And what else will go down? And t cos theta goes down. Okay, and then what we're going to have is t. Bring it over to your side. We get t cos theta equals mg. T equals mg over cos theta. And if I was to fix the other equation up, I'll just divide by 3 and I get t equals... Oh, no, you didn't. So this is where we're at here. Divide by 3. ml omega squared all over 3. Put them equal to each other. So we get mg over cos theta ends up to be ml omega squared all over 3. The m's will cancel. And okay, so ml omega squared t. So get 3g, and if you go back to the diagram on the bottom, what you would have had was our length was L, our length of our string. We would have said that that was L sine theta, yeah, and we would have had that as 2. But you can say cos theta is adjacent over hypotenuse, which is 2 over L. So that will get rid of our cos theta, which would have been L omega squared cos theta. But the cos theta itself is 2 over L. So 2 over L, and that would mean that the L's would cancel. And then we get 3g over 2 equals omega squared, and then omega equals the square root of root 3g over 2, and that's what we were asked for.